So picking this up, I want to review with you things that I know you had in General Chemistry 2, and I know it presented some challenges to you. But I hope in this context of organic chemistry, it'll all kind of fall into place for you. Now, the first KEQ, the equilibrium constant, put it up here, equilibrium constant. A constant is a number that we use. Equilibrium constant characterizes the concentrations of reactants and products. If we imagine A and B react to form C and D, and we imagine further that C and D can back react and reform A and B, we describe, and the double arrow drives it home, we're describing an equilibrium condition. A and B might react and form C and D might react and go back and form A and B. Both processes are happening. We invent a quantity that has the molar concentrations of products. Molar concentration is encoded with the square brackets. The molar concentration of C times the molar concentration of D, that is, the product of molar concentrations of the chemical products over the molar concentrations of the reactants, the product of molar concentrations of the reactants. So the size of that, the value of KEQ indicates whether we say there are more products, in which case the KEQ has a large numerator and a small denominator, so the KEQ is a big, big number, or if most of the A and B do not form C and D, if the equilibrium, the term that we use, if the equilibrium lies to the left, if it favors reactants, in that case, the numerator would be a small number, the product of small numbers, and the denominator would be a large number, the product of large numbers. So the KEQ, if it is a number bigger or much bigger than 1, we say, oh, the equilibrium in that case lies to the right, to the products. If KEQ is a fraction that's lower than 1, if it's like 0.001, we say the equilibrium lies to the left. It favors the reactants, and not too many of them actually succeed to form product. Okay? That's the first of these terms that you learned in General Chemistry 2. The second is from thermodynamics, a delta G. Delta means the change in. G superscript 0 is called standard free energy. Specifically, standard Gibbs free energy. That's why it's a G. The standard free energy change
energy change. The delta always indicates some change.
Now, that number, that value for a chemical reaction is very useful for us. We get an idea whether whether thermodynamics favors products or thermodynamics favors reactants. From the delta G value, we get a measure of that. Let me explain that these two quantities, the equilibrium constant and the standard, that superscript 0 is interpreted as standard free energy change for reaction. These two are related. Here's an equation that you've seen before. I'm going to write out delta G standard is equal to minus 2.303 RT, R is the gas constant, T is temperature. RT times the logarithm of the equilibrium constant, KEQ. It's saying that the information that's packed in the standard free energy change, we have tables of these, for example, or in the form of the equilibrium constant, they're related to each other. So one, if we have one, we can figure out what the other one is. But what's really useful to us is the following. I'm gonna erase this board and just, this is all packed in your brain, and I shall pull out for you and remind you when it's something that we need in organic chemistry. I just want to say you're not allowed to forget these. I'm going to talk now for a couple of minutes on a thermodynamic quantity called Gibbs free energy. Gibbs was a professor at Yale in the first part of the 20th century, and he studied the energetics of chemical change. He defined, I don't think he named it after himself actually, but we call it Gibbs free energy. G is a new thermodynamic, an invented thermodynamic quantity. And he said that function of state, as it's called in thermodynamics, that function of state is defined by three other functions of state. Enthalpy, I like to think of enthalpy as the heat content of a chemical substance. In other words, how much of its energy can be converted to heat, which is often what we want if we're, for example, heating a room or cooking spaghetti. We want to know how much heat can you get out of that natural gas or that gasoline. T stands for temperature, and S stands for what was, Gibbs already knew about this, but you might have forgotten. S stands for entropy, another function of state that reflects the order or disorder of a system. That is, are all the molecules packed tightly together in one little space, or are they randomly dispersed over some volume of space? Gibbs said, if we look at this combination of functions, T is also a function of state, the temperature of a sample, and we consider the difference between the enthalpy and the product of temperature and entropy, that becomes a useful quantity. So we can then consider a chemical reaction by its change in free energy, or change in Gibbs free energy, as we call it. And we say that the change in the value of G is equal to the change in enthalpy minus T. We're imagining that T is constant, so we just say T delta S. So a reaction, we can say a reaction can be characterized by a delta G value, a change in Gibbs free energy. And that is the sum of its change in its enthalpy and its change in the product of temperature times the change in entropy. So if a reaction is what we call spontaneous, if it will tend to happen given the opportunity, for example, if you throw a match at a bucket full of gasoline, the reaction will happen. And that will happen because, let's say, I'll write this down, gasoline burning in a bucket. The change in enthalpy of the gasoline is negative. Again, enthalpy is a measure, I find most usefully, a measure of the heat, the energy in the chemical system that's available as heat. Gasoline has a lot of heat content in it. When it undergoes this change from gasoline to CO2 and water, the enthalpy of the system, that is the molecules that were the gasoline, is negative. It's lost all its enthalpy that had been stored in those bonds. Delta S is the, let's say, the change in order. Well, the gasoline, when it's packed together in a liquid, all the molecules, all the atoms are really quite close to each other. After the reaction, the molecules are separate. CO2s are over there and H2Os are over there. All of that stuff gets very far from each other. So the change in entropy is large. It went from a highly ordered system to a highly disordered system. The entropy is much greater, we say, in a disordered system. So the product of a change in enthalpy and a temperature-weighted change in entropy is predictive, is useful. It's a measure of the spontaneity of a chemical reaction. So if enthalpy is negative, entropy is positive, the quantity delta H minus T delta S, which we call now delta G, the delta G is a large negative value. If a reaction is characterized by a large negative delta G, we say, oh, that's a spontaneous reaction. That's an energy downhill reaction. That will happen kind of easily. Not necessarily quickly, but easily. If in the opposite case, if the change, for example, if you invent some way to take water and split it into hydrogens, H2s and O2s, you'll become very rich and famous, but you will have achieved a way of converting, water, liquid water, into H2 and O2. That would be an energy uphill reaction. You are taking energy from the universe and packing it in to the chemical system consisting of hydrogen molecules and oxygen molecules. That would be an energy uphill reaction if the delta G is positive.